Silicon is the silent engine of the digital age, yet in its most natural state, it is a functional non-conductor. We define this as an intrinsic semiconductor, a material where electrical behavior is entirely determined by its own atomic nature, completely free of any added impurities. To find the baseline for this material, we have to look at it at absolute zero. At 0 degrees Kelvin, there is a state of perfect thermodynamic stillness, where no energy exists to agitate the atoms. In this frozen environment, every single valence electron is accounted for. There are no loose particles available to carry an electrical charge. This 3D model shows the diamond-like crystal structure of silicon. Every individual atom is locked into a tetrahedron, held in place by its 4 nearest neighbors. Moving to a simplified 2D representation, we can see the chemical forces that create this stability. Each atomic core is marked with a +4, representing the nucleus and its inner electrons. These shared electron pairs form what we call covalent bonds. By sharing one valence electron with each of its 4 neighbors, the silicon atom reaches a stable, unbroken state. With every electron occupied in a valence bond, the crystal is a dead insulator, a rigid architectural cage from which no charge can escape. The catalyst for change is ambient thermal energy. As the temperature rises from absolute zero toward room temperature, the system begins to absorb heat. This energy provides the physical force necessary to agitate the electrons trapped within those covalent bonds. This is the awakening moment. A single bond absorbs enough energy to rupture, ejecting a valence electron into the surrounding space. We call this newly liberated particle a conduction electron. It is now free to move through the lattice and carry an electric current. But the electron leaves behind a vacancy in the bond, called a hole. This empty space is its elusive partner in conduction. While the electron is a tangible particle, the hole acts as an apparent free particle, moving in direct opposition. Because each electron leaves exactly one vacancy when it breaks free, these 2 carriers are always generated in perfectly equal pairs. Thermal energy is the bridge. It transforms a dead insulator into a live semiconductor by creating these dual paths for current. If electricity is the flow of matter, how can a lack of matter physically move through a solid crystal? A chain reaction occurs. A bound electron in an adjacent bond jumps over to fill the hole at site 1. A new vacancy instantly appears where the electron vacated. Though individual electrons move tiny distances, the hole continuously drifts towards the negative potential. This distinguishes the hole current from the electron current. They involve 2 different groups of electrons, those that are free to fly and those that are still bound to the lattice. In semiconductors, we don't just track the actors, the electrons, we must also track the stage they leave behind. When an external electric field is applied, the total current flowing through the material is the result of these dual motions. Total current is defined as the combined sum of the independent flows of electrons and holes. In an intrinsic material, the mathematical balance is absolute. The concentration of electrons, Ne, must perfectly equal the concentration of holes, Nh. We represent this balance as Ni, the intrinsic carrier concentration. This value acts as a constant for a specific pure material at a specific temperature. While heat is creating these carriers, a simultaneous process of recombination is also occurring. This is where a free electron eventually collides with a hole and falls back into a bound state. This brings us to thermal equilibrium, the state where the rate of carrier generation by heat is perfectly balanced by the rate of their destruction. While intrinsic semiconductors are scientifically perfect, their carrier concentration at room temperature is quite low. For practical electronics, this is just the starting point. But the thermal awakening of silicon provides the conceptual foundation for every processor ever built. It is the process that turns heat into logic.